you don't have the cosmic catalog page, then label this absolute value, and then next to that write cosmic catalog so you know that that's where it goes. So basically, your cosmic catalog is separated from your notes because it basically it's going to continue further than this unit. So it's not just this unit's notes. Like next unit, you're going to have 2 more of those. And the next unit, 2 more of those. So I want those in one place where when it comes like finals or later on and you're trying to do something that requires use of all the functions, it's not like separated into different units, but they're all together there to summarize for you what you need. Okay? So we talked about the absolute value function yesterday. You guys put stuff on the calculator. We figured stuff out. So we should be able to fill this in with the necessary information fairly easily. So the parent function, what did we mark as the parent function yesterday for absolute value? What did the equation look like? Okay.
Y equals straight line x.
Good. Good. Our absolute value bar is just around x. Okay, that was our parent function. Nothing making it wider or narrower. This is kind of the basic thing that we compare everything else to. Then the graph. So in general, we said absolute value graphs look like what? V. Okay? And every time we see an equation with those bars, we know that our graph should look like a V. Okay? Remember that the h and the k tell you the vertex. So in the parent function, when there's no value for h and no value for k, that was like having 0 for each of those values. So our vertex was at 0, 0. And then since there's no a value in the parent function, remember that's multiplying, it's like that's a 1. So the slopes of the lines for the parent function v, every time you go up 1, you go over 1, and then same thing, but with a negative slope in the opposite direction. So then I can follow these to make my v. In each direction. So then we know as we add in h and k values, that changes our starting point. So it shifts our graph left and right with h, up and down with k. And then when we add in a values, if the a is negative, it will reflect or flip our graph over. And then if a is bigger than 1, these lines get steeper and the v looks more narrow. If a was smaller than 1, then you saw the lines get more flat, okay, or less steep, and the v looked wider. So just a little review for piecewise functions, and you guys are going to get those quizzes back today so that you can ask questions at the end about that if you want, since we have a quiz on that tomorrow, so I want time at the end to go over that. So if we were going to write this as a piecewise function, you can do that for absolute value because it's like it was one line that was stopped and cut off at a certain point, and then they started graphing another line in the different section. Okay, so we can write it as a piecewise function. So we're going to practice that so that we can recall how to do this. How many pieces would I expect? Good. 2 pieces, okay? She's stealing all your thunder. So 2 pieces. 1 piece for this line, okay, the negative sloping line that goes to the vertex, and then another piece for the positive sloping line that goes the opposite direction from the vertex. Okay? So let's focus on this first line, okay, go kind of reading the graph from left to right. The line exists, and then it stops right here at the vertex point, and then we start the other line. So what is going to be the domain restriction? Okay, this section exists when x is what? Okay, so 0 is the point. Yeah, 0 is the boundary, so it's definitely going to involve 0. And then what do we say about that branch? Good, it has to be less than 0. So this first equation I'm going to write, okay, we identify 0 as the boundary. We identify that this line is on the left side of that boundary, which is when x values are less than 0. And now I just need to write the equation of this line like I always would. So I want slope, and I want y-intercept. Okay? The y-intercept is here at 0. I can see that on my graph. And the slope, if you think about traveling from one point to another point, let's say I started at this point here, I would go to the left one, and then I would go up 1 to travel from one to the other. So that's like a negative 1, and that's like a positive 1. So when I put my rise over my run for that line, I'm getting a slope of -1. Another way you could tell is that if you could determine it was 1, okay, this line, as you travel from left to right across the graph, falls, right? It has a negative slope, so you have to be aware of that. So the y-intercept is 0, the slope is -1. So my equation for that line would just be -x, okay, because that's a slope of -1 and a y-intercept of 0. All right, next equation, this one stopped at 0 as the boundary, so this one's going to start at 0. What are we going to write as the domain restriction for it? The second piece of the graph is going to exist when x is what? Good. And because we didn't put the equal to there, and it is a closed point on our graph, we need to put it somewhere to capture that point, so we would put it here. Now, if you wrote this on your own and you had put the equal to here and not here, that would be okay too, but it needs to show up somewhere. Okay? And then same thing, we would go to this equation, and we'd want to write the equation of this line on the right side of 0, so now we're focusing on this portion of the graph. Okay? So we still see the y-intercept at 0, and this time the slope would go over +1 when it goes up 1 to get to the next point. So if I put my rise over my run, I get a slope of +1. So my equation for this line would just be y equals x, because that's a slope of 1 and a y-intercept of 0. Okay? So a little bit of review, and we'll come back to this at the end of today, and we'll put up some stuff for you guys to look at with the piecewise functions from your homework. All right, any questions about the absolute value parent function? Okay, so we know it's shaped like a V, and we know it has the characteristics, where the vertex is, and what the slope is. All right, so what we want to write down about this graph, okay, we'll talk over here in a minute, okay, important things about it. Okay? So what was the slope of the lines of this graph? 1 and -1, right? Okay. All of our absolute value graphs are made of 2 lines traveling in opposite directions. So they all have like 2 and -2, 1/2 and -1/2. One line has a positive slope and one line has a -1. So there's always kind of 2 going on there. We tend to just use the number, and then we have to use the a value, negative or positive, to determine up or down. What about the domain of the graph? We talked a little bit about it yesterday. If you're looking from left to right, okay, and thinking about traveling on this graph, are there any limitations for those x values? Can I plug in 100 for x and have a point that corresponds on the graph? Yes. Okay, so there's no gaps. There's no stopping point from left to right. So there's not going to be any restrictions on my x values that I could produce y values to go with them. So the domain is still going to be all real numbers. And this is going to be true for any absolute value function, because if the v goes up or if it goes down, you can still go left and right forever, right, and find points that correspond to it. All right, what about the range? So as you look at the graph from a different perspective, you focus more on moving up and down instead of moving left and right. Can you forever find points? Let's go up first. Okay. So for all the y values above 0, will there be corresponding points on the graph? Will the graph reach those y values? Okay. It doesn't skip any. And if I pick 100, there will be a point up here somewhere in the v that reaches 100 and a point over there somewhere up in the v that reaches 100. So it'll keep reaching those points. What about downward? What's our limitation? 0. It reaches 0, and can it reach anything below 0 in this parent function? No. Okay? So I can't go below 0. So when I write the range, I write what y can be. So if I can't go below 0, that means all the y values are greater than or equal to 0 in my parent function. So for any v, the domain is going to stay the same, because whether it goes up or down, we still have continuing left and right forever. Is the range always going to be y is greater than or equal to 0 for any absolute value function? No. Okay, what is it going to depend on? What the vertex point? Which part of the vertex specifically? the y-coordinate, y-intercept if it hasn't been shifted left or right either. So the y-coordinate specifically, and then also whether the graph is facing up or down, right? Because that vertex point, that k value, is going to be your boundary, but then you have to look at if the a is positive or negative to decide, are you greater than the boundary point or are you less than the boundary point? All right, x and y intercepts. So when we look back at our graph, what's the x-intercept of the parent function? When does the parent function hit the x-axis? 0. When does the parent function hit the y-axis? 0. This happens because we haven't done any shifting, right? So for the parent function, there's one x-intercept at 0, 0, and there's one y-intercept at 0, 0. Now, instead of writing a verbal description of the graph, what I want us to do is discuss a little bit about the x-intercepts and the y-intercepts, okay? So this is going to be a little more information. First, about x-intercepts. So first, a little reminder. No matter what kind of equation you have, how do you find an x-intercept? Good, set the y equal to 0. So no matter what shape your graph is, it's only an x-intercept if it hits the x-axis, right? All the points on the x-axis have y values of 0. So no matter what kind of function you're dealing with, if you want to find an x-intercept, you need to let y equal to 0 and solve for x. Okay? Now I want to talk about, for absolute value graphs, how many x-intercepts do you expect? Okay. So how many x-intercepts did our parent function have? 1. It hit the x-axis at 1 point. Okay. So that's a possibility. Could you hit the x-axis at more than 1 point? Well, let's look back at our graph. If it wasn't the parent function, if I was allowed to plug different numbers in but still had the absolute value v, is it possible for me to hit the x-axis in more than one spot? Okay, how could that happen? Okay, so if I change the y-intercept, so if I took our whole graph and moved it down, right, so that the v was down here somewhere, how many x-intercepts would I have then? 2. Okay, so I could have one x-intercept. I could have 2 x-intercepts. Can I have more than 2 x-intercepts? No. Okay? Even if I keep moving it down, it might cross at different places, right, if I shift it left and right. But I can't hit more than 2 times because my graph doesn't turn around again to come back to the x-axis anymore. Okay? So I could have 1 x-intercept. I could have 2 x-intercepts. I can't have more than 2. Can I have less than 1? Is it possible that my graph will not hit the x-intercept at all? Like it won't have any x-intercept. It won't hit the x-axis? Yes. How would we have transformed the parent function to get it so that there is no x-intercept in this graph? Change the k value, right? And in this case, if it's facing upward, rather than moving it down to see 2 x-intercepts, we could move it up, and we would see no x-intercepts. So for x-intercepts, a couple different things can happen. We could have none, we could have 1, and we could have 2. And it's all going to depend on whether the v is opening up or down, and then where your k shifted your graph, so if it moved up or down on the graph. Okay, so a little review of y-intercepts. So now we're looking at where the graph crosses the y-axis. How do you find them? Any type of equation, how do you figure out where the graph will cross the y-axis? Good. So we said x equals to 0, and we solve for y. Okay. Doesn't matter what thing it is. Because on a graph, no matter how crazy the graph is, if you want it to hit the y-axis, it has to have an x-coordinate of 0 at that point. So you plug in and you see what happens. Okay. Then the question here is how many? So let's look back at our graph. How many y-intercepts does our parent function have? 1. It's crossing the y-axis 1 time. Okay. Is there any way that we could transform our graph and get it to cross the y-axis more than one time. Okay, if we turned it sideways. So then it's not a function, but this is a really good point. So if we changed the absolute value bars to be around y instead of around x, that's when it will look like it's sideways, okay? But then it breaks the function rule, right? So those are absolute value graphs, but not absolute value functions. You guys get what I'm saying? Really super fine line, but very good point, okay? So if we turned it sideways, it could definitely have 2, but that's not a function, so we're not considering it in this family right now. Okay, so if we face it downwards, is that going to change the number of y-intercepts that we have? Okay, so if we decide, here you go, face it downward. Okay, so the way I drew it, it still just has one y-intercept. Is there any way for me to flip it, make it wider, make it narrower, move it left or right, move it up or down? Is it ever going to cross the y-axis more than one time? No. Is it ever going to not cross the y-axis? No, because the problem is these lines go forever left and right? So even if you take this graph and you move it way over here, eventually that part of the V is going to keep going, and it's going to hit the y-axis still. Okay? So how many y-intercepts are you going to expect for every absolute value graph? One and only one. Yeah, so you'll plug in 0 for x, you'll solve it, and you'll always get one answer. Okay? With your x-intercepts, it's going to be trickier, right? You'll plug in 0 for y and you'll solve it, but it's possible that there are none, there's 1, or there's 2. Okay? All right, so in order to find x and y-intercepts, you guys have to remember how to solve absolute value equations. So on the back side of the Cosmic Catalog, there was the 6 problems that you guys graphed last night for homework, and then below that there were 4 solving problems. If you don't have it, just write down the 4 solving problems on this page to remind you, like on the page you're taking notes on, to remind you how to solve them. Okay? All right, and the idea behind solving absolute value problems is think about the simplest absolute value problem and wanted it to equal 5. Okay? The absolute value of some number turns out to be 5. What could that number be? 5 or negative 5, right? Basically, whatever's in here has to have the same value as what's out here if it's already positive, or the same number part, but just the opposite sign. So we basically say the stuff in here either equals that positive number, or it equals the opposite of it, and the bars changed it positive. Okay? So if we take that same idea and we take something complicated like 2/3 x minus 6 inside the absolute value bars equals 42. Again, who cares how complicated the stuff in there is? You're saying the absolute value of something equals 42. That means the something that's in here is either exactly equal to 42, or the something that's in there is exactly equal to negative 42, and at the end the bars are making it positive, right? And so then I'm just going to copy down the something that was in there. So the 2/3 x minus 6. So basically, to solve absolute value equations, you set up 2 equations, the 2 possibilities that could happen without the absolute value bars. You don't need the bars anymore because you said the bars mean that either this happened or this happened, and now we can solve it like we do in Algebra 1. Okay? No, they can be on that one. That's okay. So here, if we add 6 to both sides, we'll get 2/3 x equals 48. And for those of you that still hate fractions, get used to them, okay? So we would want to multiply both sides by 3/2 because the 3's would cancel and the 2's would cancel, and we would just have left x. But that means we also need to multiply 48 by 3/2. Okay? So remember with fractions, okay, you have to put a 1 in the denominator. You multiply straight across. But if you don't want to multiply big numbers, remember if there's a common factor from any factor in the numerator, and a common factor with something that's in the denominator, you can cancel that common factor out. So I can divide 2 by 2 as long as I divide either 3 or 48 by 2 also. Okay? So really this is the same thing as 24 times 3, which is 72. Okay? And so here, okay, same idea. I would add 6 to both sides. So I would get 2/3 x equals negative 36. And then again, I'm going to multiply by the reciprocal of that fraction in front of x. So multiply by 2. Okay, so 2 divided by 2 is 1, and 36 divided by 2 is 18. So this is like 18 times 3, which is 54. So x is either equal to 72 or negative 54. So this function, if we graphed it, would have two X-intercepts, okay, at 72 and negative 54. It wouldn't look like that when you graphed it. It would have looked like this, like y equals 2/3 x minus 6 minus 42. Like if you moved the 42 back to the same side as the absolute value, so everything was together, so you had like a's, h's, and k's. Okay? I know this isn't exactly where we like a, but we could take care of that. If you had an equation like this and they said find the x-intercept, you would have set y equal to 0, and then the first thing you would have done was move the 42 to the other side, and you would have had this equation. You would have solved it, and you would have got these two x values. So these two x values would have been the x-intercepts for an equation like this for a graph. Okay? So I'm reviewing how to solve and reminding you guys that if you're asked for x and y intercepts, you know how to do that. And then you have to remember how to solve when it's an absolute value and not just a line. Okay? All right, what do you guys think about the second one up here, number 8? It's 8 because the worksheet had 6 graphs. Okay, 7, 8. What are we going to do? Lila? Say it louder. Okay, good. So option 1 is to set up two equations, right? Yeah. Yeah. Okay, and then you would solve. Now, in this case, if you set up those two equations and you solve, you get two answers, and when you plug them back in, they do not work. Okay? This problem is actually a little bit trickier. Okay? Let me write a simpler problem. What if I said this? The absolute value of x equals negative 6. What number is x? 6. So the absolute value of 6 is negative 6? How does absolute value always turn out when you calculate it? Positive. So is it possible for me to plug a number in here and get negative 6? No. Okay? So is it possible up there, no matter how complicated the inside is, 5x minus 4, no matter how crazy they write stuff on the inside, if that is all surrounded by absolute value bars, is it possible for it to equal negative 6? No. So you can totally solve it the normal way, but then be really diligent about checking, because then your checking is going to tell you if it actually works or not. So if you solved it the normal way, you would get answers. But if you plug those answers back in and try them in the equation, they don't work. The reason they don't work is that you could see from the beginning this equation has no solution, because there is no way that an absolute value is going to equal a negative number in the end. So if you isolate your absolute value, no matter how much crazy stuff is in here, and it says the absolute value is equal to a negative number, that equation has no solution. There is no way I can give you something in here, no matter how crazy it is, because the last thing you're going to do is turn it positive. There's no way it's going to match the negative value on the other side. Okay? So again, you either need to learn to recognize that, or if you're going to be like autopilot and every time you see absolute value bars, you're just going to start solving, you need to check all your answers at the end, okay, to see if they worked or not. Now, what this means is that if we had had this equation, 5x minus 4, say you brought the 6 back to the other side, say we were graphing this absolute value equation, how many x-intercepts would you guys expect this equation to have? So we would plug 0 for y, right? And then we would solve. When we plug 0 for y, and then we move the 6 over, we get the same problem we were solving right here. This problem had no solution, so how many x-intercepts do you think this graph had? Not 2, 0, okay? That's why it had no solution. You tried to set y equal to 0 and solve the equation, but when you set y equal to 0 and solved, it's not solvable. That's because it's not crossing the x-axis. Okay? If there was 2 intercepts, you would have gotten 2 solutions like we did in the first one. Okay? If there's 1, you would just get 1. All right. Why are 9 and 10 slightly more complicated than 7 and 8? Yeah, there's an x on both sides. So there's a variable inside the absolute value and outside the absolute value. First thing you have to do is get the absolute value alone. So like in number 10, I would want to divide both sides of the equation by 5. Okay, because I don't want to start solving until the absolute value is completely isolated and alone. So if we divide the left side by 5, we get 4x minus 1 still in the absolute value bars. When we divide the right side by 5, we're going to get x plus 8. Is that okay with everybody? So all I did was divide both sides by 5. I don't want to start separating out the problem until I have the absolute value completely alone. So if this was a positive number on the right side, like if this was just 10, we would continue this problem by removing the absolute value bars and splitting it into the 2 situations, right? That the stuff inside of here either equals 10 or the stuff inside of here equals negative 10. If this was a negative number on the right-hand side, what would we do? That we would know automatically there was no solution. Okay? Because the right-hand side is wacky and has x in it, do we know whether it's positive or negative? No, because we don't know what x is. So here's what we have to do in these situations. We have to pretend like it's positive and keep solving like we normally would if it was solvable. But then at the end, we have to go back and check and see if we were solving a solvable problem or an unsolvable problem that really didn't work. Okay? So we're going to split this into its 2 parts, even though we don't know if it has a solution or not. So one is going to say 4x minus 1 equals, we're going to pretend like that's a positive thing, x plus 8, exactly what it says. And the other one is going to say 4x minus 1 equals the opposite of that. What is the opposite of x plus 8? Yeah, the opposite of x plus 8 is negative x minus 8. Like the opposite's been applied to everything that was on the other side. All right, so then we have 2 equations to solve. So I'm going to subtract x from each side, add 1 to each side. So I get x is 3. I'll do the same thing here. And I get x equals negative 7 over 5. So then I have to plug them back into my original equation and check. Because we don't know if we were solving something that actually has a solution or not. All right? Sometimes one will work, sometimes both will work, sometimes none will work. You plug it back into the very original equation. Okay? So for 3, I'm basically asking myself, if this is true. Okay, I put 3 on both sides, and I want to know if it's true. Remember, when you're checking, don't move stuff side to side. You're seeing if the original equation works out or not. You calculate everything on the left side. Separately, you calculate everything on the right side, and then you compare and see if they match or not. Okay? So 4 times 3 is 12. 12 minus 1 is 11. So this is 5 times the absolute value of 11, which is going to be 55. On this side, 5 times 3 is 15, and 15 plus 40 is 55. So 3 is a good solution. Okay? They matched. The next one's going to be a pain in the butt because it has a fraction. Okay? I don't like it either, but I got to know if my answer's right, so check it. All right, I'm going to calculate the right side first because the fraction cancels. So feel more confident about that. So 5 times negative 7 over 5, the 5s will cancel out, and I'll just have negative 7 plus 40. So I know that on the right side, I don't really need, it's negative 7, sorry, plus 40. So I'm getting 33. And then the question, is that going to work out on this side as well? So if you need to do some fraction math on the side, do some fraction math on the side. I don't know. 4 times negative 7 over 5 is negative 28 over 5. Okay? I don't know. So I'm going to take, so you guys have negative 28 over 5 minus 1 inside the absolute values. Okay? So if you struggle with fractions, you know that if you want to add two fractions together, they need a common denominator. 1 is 1 over 1, right? So if I wanted to have the same denominator of this, which is 5, I can make that denominator 5 by multiplying by 5 as long as I do the same thing in the numerator. So the denominator will be 5. And the numerator will be whatever negative 28 minus 5 is, which is negative 33. And that's being multiplied by 5. Here the 5s will cancel. Okay. This will have been made positive by the absolute value. So then the final answer on this side would be 33. So that one works too. So this answer is good as well. Okay. But don't think like, oh, she checked that hard fraction and it worked. I don't have to check every time. It'll work every time. It won't, okay, because it totally depends on if when you plug x back in, you had a positive or a negative number on this side. Most likely if it was a positive, it's going to work fine. But if it's a negative, it would have never worked if we knew the number. We wouldn't have even done the problem. We would have just stopped. Okay? All right, so you guys can finish number 9 on this handout before we stamp homework tomorrow. We probably won't end up stamping what you guys did yesterday today. And there's another handout posted on Canvas that's just more practice with absolute value. So when you guys come in tomorrow, we're going to do your quiz on piecewise functions, and we're going to go over all your absolute value homework. So what I want to do right now is pass back all the papers that I have for you guys. I have like your problem of the days, and then I have your linear quizzes. I just recorded that you did corrections and gave you classwork credit for that. And then I have your piecewise function quizzes so that you guys can look at those for the remainder of our time in here. Okay?